Hi, I'm Anna Savina, and I'm a head of marketing here at Archetype AI.
And I'm Jamie. I'm a co-founder and chief scientist.
And today we have a very exciting deep dive into our new research paper focused on adaptive world models.
Think of a skilled technician or machine operator, somebody who's been working with an engine or a particular drilling rig for a long time, maybe decades. Over that time, these technicians and operators have built up a really good mental model of the way that these machines operate, to the point where they can, hear the sound that the machine is making or feel a couple seconds of the vibrations the machine is generating and instantly know what state the machine is in, whether it's behaving normally, whether something is faulty, what kind of fault it is, how it got into that state. That kind of mental model of machine behavior and physical behavior is essential for operating and monitoring these physical industries, but none of the AI models today are able to replicate it.
And I know we're introducing this new approach to thinking about world models, a paper that outlines our point of view. But beyond the academic community, what does it mean for people who are interested in AI or using AI for daily operations?
Yeah, it has huge implications, I think, for practical everyday life. The world's economy is 85% comprised of physical industries, which is huge. So manufacturing, industrial, energy, these make up a huge percentage of the economy, and just our everyday society is built upon these industries. And so the physical machinery and systems that run these industries are essential to keep healthy and operational. The cost of downtime of any particular machine could be in the order of millions per day. And really, if we think about the annual cost of operational uncertainty in general, could be on the order of trillions. And so it really is an essential component of our everyday life and practical operation of society to keep these physical industries in a healthy state.
But Jamie, I know there are also a lot of tools right now and industrial AI solutions that are specifically focused on predictive maintenance or anomaly detection. This is not very new. So I'm curious how Newton can be, what's different about Newton and how it's approaching these challenges that industrial operations are encountering.
Yeah. So understanding physical systems and physical machinery is definitely not a new problem. I mean, people have been trying to solve this for over half a century, all the way from classical systems theory, dynamical systems theory, to more statistical techniques, and as you say, to ML and AI today. And fundamentally, the limitation of all these more classical techniques is that they're not scaling to the broad diversity of different machines and systems that exist in our industries, as well as the different deployment environments in which we see them, proliferating today. And so what that means is that for each particular system and each particular deployment, you have to invest a lot of hand engineering resources, a lot of time and cost in order to build these solutions. So what we're offering at Archetype AI is Newton as a foundation model. So one model that can actually generalize across all of these different systems by having an empirical understanding of the underlying physics and then adapt to each particular deployment or machine.
And another solution, I think, that is pretty popular is digital twins, because it's replicating real-world environment and allows for simulation that can guide people to certain insights or certain discoveries around the world. How is our approach is different from digital twins?
Yeah, digital twins are certainly very powerful, but I think they suffer from the same cost and resource-intensive setup process that these other more classical techniques do. Basically, that you have to approach the building of a digital twin with a lot of domain understanding, with predefined physical laws, behavior already encoded into the model of the physical twin. And so what that means is that they're fundamentally very difficult and time-intensive to scale, that you have to build each digital twin for each specific machine in a very custom, bespoke way, and that takes a lot of time, effort, and engineering resources.
I see. That makes sense. I'm curious also, I know that the world model space is also it's booming, it's growing right now, and there are different approaches. Like recently, Fei Li wrote this piece about World Lab's approach to world models. How are you thinking about those different approaches, and what makes Newton unique in this kind of environment?
Yeah, I think there are a couple differences. A lot of the world model work today is very vision focused. And so they're fundamentally learning about the way that the world works through pixels and through visual imagery. What we see in industry and in a lot of practical situations is that there's a huge preponderance of different sensor types and sensor modalities that people are using in order to monitor and otherwise have insight into their equipment. And basically, every modern machine, is continuously measuring its internal state, its external environmental factors through a very broad variety of, motion sensors, gas sensors, temperature, RF, things that are very non-visual and might not be even things that we as humans can directly perceive. And so I think there's a need for world models to be able to generalize and understand this broad, long tail of different sensors in order to accurately and precisely understand the way that different physical machinery operate. I think the other main difference between Newton and what we see in the current world model dialogue is that a lot of world models are centered around simulation. So being able to build, realistic, simulated, rendered environments or simulated behaviors. What we're actually interested in is in operational understanding of these machines. And so these world models have to be constructed and deliver insight into the way that these different machines are behaving, their current operational state in a way that is interpretable to human operators, how they got into that state, what is the root cause of having a fault, what is going to happen in the future. All of this, I think, is somewhat beyond just a continuous representation, which is what some world models are defined as. And it's also somewhat different from the ability to simulate what is going to happen in a hypothetical situation.
So the alternative we're proposing is adaptive world models. Tell me a little bit more about your research process.
Yeah, so the main premise is that we believe that machines can understand their own internal behavior simply through observation, so through their sensor measurements, and that this understanding of their behavior doesn't have to be predefined or, instilled by humans. And from that, machines can discover their operational, what we call ontology, so a vocabulary of their different states and the way that these states interact with each other simply by observing and measuring these physical conditions.
Tell me a little bit more about the architecture of the model.
Yeah. So under the hood, Newton has a form of a pre-trained physical world model, which has learned basically forms of empirical physics. So we pre-trained it on a very diverse range of physical sensor measurements, measuring a large diverse set of physical quantities, temperature, vibrations, electrical behavior. And so through observation, this foundation representation model has learned the underlying structure that's common across all these different processes. And then when the model's applied to any specific machine, within that representation space, the embedding space, it can map out the manifold of the behavior of that particular machine. And from there, discover the various discrete states and operational regimes of the system, as well as the transition behavior between both states.
How long does the training take?
The model is fully pre-trained, which means that out of the box, you can already apply it to your data. So as sensor data comes in from the machine, it's already mapping it into this latent space through these frozen weights of the foundation encoder. What is useful is having a little bit of historical data so that we can associate names to those states that are discovered in an unsupervised way. And so the discovery of the states themselves is not through labeled or historical data, but the assignment of a label in a human understandable format is.
We talked about digital twins earlier, and I know that their deployment can take up to 6 or even 9 months. I'm curious what it looks like when you're deploying Newton. What is the timeline that we're looking at?
So fundamentally, because we have a foundation model which comes pre-trained, and we don't have to do all this per system engineering, we can take just a little bit of historical data from the customer to see the adaptation and then deploy a solution on the order of less than a month. Once the model is deployed, then it adapts to new incoming data that it observes through its sensor modalities in order to make sure that its understanding of behavior is up to date and relevant to that particular deployment.
And what does deployment entail besides the timeline? What are the resources you need and what is the tech stack required?
Usually, our customers have some historical data that they're able to provide that is used to seed the adaptation based on other similar machines or other deployments of that particular machine. So this can be as few as a few n-shot examples of the states of interest, or any amount of data that the customer might want to provide. Then practically, we have a platform for building solutions or agents using our model. That platform basically accelerates the development of these solutions and then deployment to wherever they want the model and the inference to run. That can be in the cloud or on-prem or ultimately at the edge.
Great. So lots of flexibility in terms of deployment.
Exactly.
Yeah, and there was I'm curious also, what's the vision for the next couple of years? Where do we go from there, and how do you see the model evolving?
Yeah. So I think what we're focusing on currently is the horizontal generalizability of the model. So really demonstrating at scale and through practical deployments that our model can generalize to diverse types of sensors, diverse types of machines, and physical assets. From there, I think what we want to cover is, vertical capabilities. So not just doing things like operational state monitoring, but also adding in layers of interpretation and explanation through natural language interfaces, for example. This then makes it useful and actionable to any sort of operators or technicians who might want to use it. And then ultimately, what we aim to provide is not just insights, but also to action and decision. So enabling autonomy, for example, and really decision-making at scale.
So, Jamie, I know that we have this recent launch with Newton agents, and there is this adaptive world models roadmap. But how do you see the model evolve over the next couple of years?
Yeah, well, we expect the base foundation model to continue to improve, especially as we increase our training corpus across more and more diverse types of sensors, more diverse types of physical domains. And so we believe the fundamental capabilities of the model will continue to increase. Because of adaptation, we believe that each machine will continue to get more and more insight and understanding of its behavior year after year. And so ultimately, what we think we're providing at Archetype AI is the ability for any physical asset to be intelligent.